Our next speaker, Jack is so closely associated with the top 500, but there's so many more things that he should be recognized for. I'd just like to read just a couple quick things about Jack that I'm always so impressed with. But publishing approximately 300 articles, papers, my gosh, when do you get time to play golf, Jack? He's been awarded the IEEE Sid Ferdenbach Award for his contributions and co-authoring of several books, application of high-performance computers using innovative approaches in 2008, recipient of the first IEEE Medal of Excellence in Scalable Computing. We are very honored to have him here today. Please join me in welcoming Jack D'Angara.
Well, thank you very much for that kind introduction. I'd like to add to congratulate John here on the meeting. I think of supercomputing as having a pulse, and this is one of the pulses of supercomputing. The other one would be the meeting in November, and then the meeting in Germany in June. So you're to be complimented. And I just realized that 25 years for this meeting is longer than SC, the SC meeting itself, which is a tribute to your ability to pull this off. So I'd like to talk about architectural aware algorithms and software for Peta and Exascale. I'd like to try to make this interactive. So if you have a question during the talk, ask the question, and I'll try to field it. I have, 30 minutes from now, is that right? Okay. Okay, so I'm going to take a look at high-performance computing through the eyes of some data that we've collected over time. So this is the top 500 data. We can argue if this is a good thing to look at or not from a standpoint of a benchmark. I don't want to have that argument now. I'm happy to argue with you later, but if we have that argument, I'll probably want to be on your side. Okay, that's the first thing. So the top 500 is a list of the 500 fastest computers. We collect this list twice a year. And to rank the computers, we run a benchmark. And that benchmark is called the LaPack benchmark. Basically, you want to solve AX equals B, solve a linear system of equations. Make that, use the best implementation of Gauss elimination with partial pivoting, use 64-bit floating point arithmetic, solve the biggest problem you can on your computer using as many processors as you can, and we're going to look at the rate of execution, right? The performance that you get out of it. And think of it like this. As you increase the size of the problem, the rate of execution goes up until you reach some asymptotic point. And we want to capture the asymptotic point for your machine. That's what we're going to register. So that's done twice a year in November and also in June. And if you're interested, there's a website that contains all the data. So in some sense, this is a snapshot of high-performance computing going back to 1993 when we started collecting this data. And the way to look at this is this green line here represents the guy at position number 1, so the fastest computer. Today, that's a machine at 2.57 petaflops. The blue line here is the machine at the bottom of the list. That's the guy that just made it on the list, machine number 500, and it's at 31 teraflops. And you can see what's, and let me just mention this red line here is the sum of the 500 machines. So that's an Excel sheet computation, right? You just add up the 500 machines and plot that point. And today we're at 44 petaflops of accumulated performance, if you will, on the top 500. There's a lot of interesting things. The slope of the line here. So the slope of the line, we might think behaves like Moore's law. So it turns out the slope of the line is doubling every 14 months. So it's doubling faster than Moore's law would have predicted. So why would that be? Well, it's because of parallel processing. Every time the machines come out, they come up more processors, and they're sort of accelerating things. You know, the guy at the bottom of the list today, that was equal to the sum of all the machines not too long ago, back in 1997. So that's an impressive number. You know, this exponential growth thing is really quite impressive, and I have a hard time sometimes getting my hands around it when it affects the things I use on a daily basis. You know, again, going from number 1 to falling off the list takes about 6 to 8 years. So going from the fastest computer to being something where you want to turn it off and get rid of it for scrap metal takes about 6 to 8 years. And you know, my laptop, very impressive computer. This is a dual core Intel processor in this machine, and I can run the benchmark on this laptop. And when I do that, I get a few gigaflops out of a laptop I use mainly for reading email and giving talks. So that's quite a striking thing. And again, you know, when I look at that, not too long ago, that would have been one of the machines on the list. So quite striking results. And let me just go one further. My iPhone. So my iPhone, I can run the benchmark on it. There's an app for that, so you can download that app and run it on your iPhone. You get 40 megaflops out of it. 40 megaflops. That's incredible, right? Out of a phone, that a few watts out of it. So that's a very impressive thing. So things are changing. This is a list of the top 10 machines today. So we're looking at the very top of the list. The way to read this is the machine at position number 1. It's the National Supercomputer Center in Tianjin that I think Thomas mentioned it, the Tianhu 1A. It's produced by the National University for Defense Technology. So they were the people who produced the machine. They did the integration of the system and also built part of the hardware. And the hardware is composed of Intel processors, NVIDIA processors, and a custom interconnect. So they actually built the interconnect, the thing which you transfer data between the nodes in the system. It has 186,000 cores, the way I count cores, and we'll talk about that a little bit later. So 186,000 cores, 2.57 petaflops is the achieved performance, and that's 55% of the theoretical peak. Right, so the theoretical peak is an artificial number. Look at the cycle time, look at how many operations you do per cycle, look at how many processors or cores you have in the system, and that'll give you the theoretical peak. And they achieve 55% of the computation. So if we just scan down the list, a few things are sort of striking in the list. 2 machines in China, number 1 and number 3. Both of those machines are based on Intel plus NVIDIA GPUs. The machine at Shenzhen is actually built on top of InfiniBand interconnect, not built on a custom interconnect. There's a machine in Japan at the Tokyo Institute of Technology, again, Intel plus NVIDIA parts plus InfiniBand, same kind of story. Number 2 machine, number 5 machine, number 7, and number 10 are owned by the Department of Energy. So the Department of Energy is a big investor in terms of simulation for advancing computing, or advancing science, and they're a heavy investor in terms of high-performance computing. So they hold a large stake in terms of the US component of high-performance computing. There's a machine here in Germany at the CEA, and a machine in Jülich in Germany. Looking at the number of cores on these systems, you see large numbers of cores, hundreds of thousands of cores, 250,000, or actually more than 250,000 on the machine in Jülich. The other thing to notice here is the percentage of peak. Just looking at it, the machines that have GPUs, accelerators, are seeing roughly 50%, around 50% of the theoretical peak performance out of those machines. Other machines that are based on homogeneous processing are seeing something on the order of 75 to 80% of the theoretical peak. So that says something about extracting performance from these machines. Hybrid machines is going to be harder to extract performance when you have a GPU plus commodity core based. And this is we'll call it an easy benchmark, something easy to extract performance. This benchmark is really based on matrix multiply. And I'll point out what the real problem there is in a moment. And as you know, these machines are very power hungry. So here's a measure of the power used under load for these machines. So it's about 4 megawatts of power for the machine in China. The machine at Oak Ridge is about 7 megawatts of power. A megawatt roughly is 1 megawatt per year is about $1 million if you run it. The other way to think of a megawatt, it takes about 1,000 houses to use a megawatt of power. Okay, so those are two numbers. The other thing to look at here is the efficiency. So this is flops per watt. So you want to have a very high number here. You want a lot of floating point operations per power used. And the machines that have the most efficient machines are the GPU-based machines. So we see the machine in China having 637 measure, the machine in Tokyo having 850 as a measure. So again, the GPUs are coming to play here in terms of being able to give you good efficiency. I just stuck in here on the bottom here, the guy at the end of the list, number 500. It's a machine in the UK. It's a cluster. It's based on Intel parts plus a gigabit Ethernet. So this is a very low-cost way of building a high-performance machine, if you will, based on GigE. And notice that the efficiency here is about 53%, and that's because of the slow interconnect associated with that machine. But notice that the guy at the bottom of the list has 6,000 cores in it. So again, large numbers of cores, even at the very bottom of the list for these machines. This is a chart which tries to visually give you a handle on where the computers are. So there are 500 rectangles here, and the rectangles are colored by country, and the size of the rectangle reflects the performance that they achieve for the benchmark. So the fastest one is this one here, the China machine. This is the number 2 machine in the US. So US is quite dominant, 274 machines on the top 500 list. China's number 2 with 41 machines on the top 500, which is quite striking. A few years ago, they had zero machines on the top 500 about 6 years ago. And today they have the number 2 position. So that's an incredible sign that they're about the investment that they're making in terms of high performance computing. And remember, that investment is just not buying Western parts. They're starting to construct components of the machine, and I think we'll see more of that evolving in the near future. Notice that Germany, Japan, France, and UK have roughly the same number of machines, which I found kind of interesting. Okay, so that's a quick look at that. If we want to take a look at where things are going in the future, I've just plotted here the number 1 machine and the number 5 machine, and we're going to extrapolate. But before we extrapolate, if we just decorate the chart with the top 500 winners, sorry, with the Gordon Bell winners. So Gordon Bell, a number of years ago, provided some of his own money to try to promote the use of parallel computing for scientific applications. And he said he would give away, I think the number is $10,000 of his own money. Some of that would go for, half of that would go for the best application that beat last year's winner in terms of the use of parallel processing. So there's a lot of competition for this award because of the money and because of the prestige associated with it. If you plot the winners of the Gordon Bell Prize, they fit pretty closely with the LaPack number 1 entry, which is some kind of correlation. I guess the Gordon Bell winners look a lot like the algorithms that are used in linear algebra. If we take a look at extrapolating this, we see that it says that we get to 10 petaflops roughly in 2012. We get to 100 petaflops in around 2015 or 2016, and it says we get to an exaflop, 10 to the 18 operations per second, roughly in 2018, 2019. Okay, so that's sort of a path that we're on. You know, that's been true for the past 18 years, and you know, maybe it'll continue into the future. We know about 4 machines that are going to be deployed in the U.S. that have 10 petaflops or more in the next year. Okay, so this is the plan within the U.S. There's a machine that's going in at Oak Ridge National Lab. It's a Cray design with accelerators that'll be around 20 petaflops of peak performance. There's a machine going in at Livermore that'll be based on the Blue Gene Q architecture, around 20 petaflops peak performance. There's a machine going into Argonne National Lab, which is based also on the Blue Gene Q architecture at 10 petaflops. And there's a machine at the University of Illinois that's been funded by the National Science Foundation, which is going to be around 10 petaflops based on the IBM Power 7 architecture. So we're going to hit that mark, that second mark of a 10 petaflops, roughly in 2012 for the previous list. And how that unfolds in the future is a little bit unclear. If we take a look at the architectures, we take a look at the architecture that we have for the fastest machine in the US. This is the machine at Oak Ridge National Lab. Its performance, peak performance is around 2 petaflops. It consumes around 6-7 megawatts of power. It has about 1/3 of a petabyte of primary memory. The node performance is about 125 gigaflops. The speed at which we can move information around the node is about 25 gigabytes per second. It has 12 cores is what a node is made of, two AMD sockets, 6-core sockets. It has inter-node communication about 3.5 gigabytes per second. It has concurrency about 250,000 cores total. And the mean time between interrupts is measured in a few days. About 2 days is what people say for the mean time between interrupt for that machine. If we take a look at what's planned for the Exascale machine, the Exascale machine has some constraints imposed on it. And these are perhaps artificial constraints, but they've been imposed on the design of an Exascale machine. And the constraints relate to the amount of money that can be spent, and also the amount of power that the machine can consume. So the constraints are that we're going to cap the machine at $200 million, and the power constraints are at 20 megawatts. So 20 megawatts for an Exascale machine. Today we're at 7 megawatts. That's the US fastest machine, the Cray machine. So that's going to be a pretty outrageous power constraint, I would say, in terms of the machine. But that's the constraints that have been placed there. Whether or not that will actually be met is a little unclear. So $200 million. For $200 million, you're going to spend half of your money on memory. That's the way the story goes. And the semiconductor guys have a pretty good roadmap of where memory is going. And we can be pretty precise as to how much memory you can buy with $100 million. And for $100 million, it says that you can get somewhere between 32 and 64 petabytes of primary memory in your machine. So that's a fixed point. And then from there, you can sort of unfold the rest of the machine. The rest of the machine has these characteristics. A node is about 15 teraflops. The intercommunication will be between 2 and 4 terabytes per second. The node concurrency is about on the order of 1,000 to 10,000 cores or threads of execution. We're going to have internode communication here between 200 and 400 gigabytes per second. The total concurrency in terms of threads of execution is going to be measured in billions. So billions of threads of execution have to be managed with an application using this machine at scale. And the mean time between interrupts is thought to be around 20 hours, is what people are thinking. So there's a number of constraints that this machine really imposes on its effective use. We're getting 3 orders of magnitude in terms of the performance going to Exascale, so that's a good thing. The system memory, however, is only going up by 2 orders of magnitude. And again, that's imposed because of the cost constraint. 2 orders of magnitude is going to have an impact on the kinds of algorithms and applications we run on this machine. Today we enjoy something called weak scalability. So as we increase the size of the machine, we increase our applications in proportion so that things can grow and scale with the machine. So now we have a ceiling on the machine, so we're not going to be able to grow those applications in the same way that we've grown them in the past. And that's going to put some cap on the size of problems that we can run and dampen the performance that we actually see out of those applications. The node memory bandwidth is something which is only going up by 2 orders of magnitude, something that's going to really affect the overall performance that we see out of the node. The concurrency is going up by 4 orders of magnitude. And that's something that we're really going to struggle with in terms of the programming models that we have and the execution models that we currently have within our application space. You know, today our applications are built on Fortran and C using MPI. And that's just not going to work at these levels of concurrency. And then the mean time between interrupt at 20 hours says we're going to lose an order of magnitude, and says perhaps we have to pay more attention to fault tolerance and look at resilience in a different way than we have in the past. In terms of what the machines might look like, this is 2 paths that people talk about to get to Exascale. We have to get to 10 to the 18. So one way to get there is to think about lightweight processors, something like a Blue Gene processor, Blue Gene core. A gigahertz would be the cycle time of that, so that gives us 10 to the 9. We have 1,000 cores on a socket, that's 10 to the 3, and then we have 1,000,000 of these sockets in the machine. So 10 to the 9 times 10 to the 3 times 10 to the 6 gives us that 10 to the 18 number that we need to get to Exascale. In a hybrid machine, think about a GPU or an accelerator playing along with that machine. We got a processor, again, about 1 gigahertz. We have 10,000 of these FPU sockets in the machine, and then we only need 100,000 of those sockets to build out the complete system. Again, 10 to the 9 times 10 to the 4 times 10 to the 5 gives us that 10 to the 18 number that we need to get to exascale. So those are two potential designs for a machine. Will it look like that? I don't know. When we were thinking about petascale computing, Thomas showed a slide about the original petascale meeting that was had. You know, there were many designs for petascale machines, and some of those designs don't look like anything that we have today in our existing petascale machines. So there's a number of factors here which really cause us to rethink and redesign our software in order to effectively use these machines. We have this very steep ascent as we go from Terra to Peta to exascale machines. Taking a look at the number of how the number of cores in the top 20 machines on the top 500 have grown over the last few years, you see this really great, this very steep path here. So we have an average of 125,000 cores in those top 20 machines today. We have this extreme parallelism that's coming about, and a hybrid design which is going to give rise to a necessity for looking at how these algorithms can effectively use that and have to change in order to use that. We have this tightening of the memory bottleneck that I mentioned, where we're going to lose an order of magnitude basically, and it's going to really focus our attention on communication much more than we have today in terms of the movement of data. And we have this necessity to look at fault tolerance and look at how we might effectively deal with failure. You know, checkpoint restart is really not going to be an option on these machines. We can't afford 4 hours to roll out all of memory to do the checkpoint, and then another 4 hours to roll the thing back in terms of a failure. So we have to come up with different strategies to effectively deal with that. I just want to spend a moment talking about the accelerators. Typically today what we have an Intel plus NVIDIA accelerator. So there's a host processor here, say an 8-core Intel processor. It has its own memory, and then an accelerator, perhaps a NVIDIA Fermi processor. The NVIDIA people say this has 448 CUDA cores, but the way the machine actually operates, 32 of those CUDA cores are executing a single thread of execution. So I really think that we should gang them in terms of 32, giving us 14, quote, cores on that NVIDIA board. So that's in fact the way we count cores when we look at the GPUs. 32 are ganged together to do one thread of execution. That gives rise to 14 cores overall for that system. The way these machines are connected is through a DMA connection. Electronically, that's realized by a PCI Express interconnect. That PCI Express has a certain bandwidth associated with it. So what typically happens is the host processor moves data over to the GPU. It tells the GPU which operation to do, and then the host processor goes off and does something else, asynchronously operating, and then looking to see if the results are ready from the GPU, and then going back and extracting the results back to the host processor from the GPU. In this case, the accelerator has a potential theoretical peak of half a teraflop. 500 gigaflops is the theoretical peak in double precision for that accelerator. This path over here allows for 1 gigaword per second of data movement. So we have this real strangle point here about moving data from the host over to the GPU. You have 1 gigaword data movement per second, and this guy here is capable of executing at 500 gigaflops. So you've got to get a lot of reuse of data. You've got to get a lot of operations, squeeze a lot of operations out of that data that you move in order to get the performance up. Otherwise, you'll be spending all of your time just passing data back and forth between the two components of this machine here and operating really as if you only had 1 gigaflop worth of performance on that GPU. So if you pass data over, just get one operation out of it and pass it back, you're going to be dead in the water. Looking at the GPUs today, there are 17 GPU-based systems on the top 500 list. So while we think a lot about GPUs and there's a lot of hype about it, there's really only 17 out of the 500 machines are based on GPU technology. This GPU stuff, we've seen this before. You know, I've been around a long time. We've all been around a while. You know, floating point systems had an attached processor. This is the same thing, attached processor to your main processor. Intel had a math coprocessor back when the processor itself wasn't really capable of doing floating point operations, and you had to pass data over to that processor and collect the results. Waytech had a math coprocessor that I think went along with the Spark architecture in the early days, again, where you passed information over to it. So we've seen this thing before. This is not a new idea. And it's all about communication, the speed of communication in proportion to how we move data along. We've seen some of this from Stephen's talk this morning. Future systems are likely to be hybrid in design. Accelerators are attached today, but there's going to be more integration of the accelerator into the processing cores themselves. With the mic architecture that was mentioned for Knight's Ferry and Knight's Corner that's coming, there's going to be this integration that takes place of those cores being embedded in the actual host core itself. AMD has a product which will be available soon, we think, which again embeds the graphics component into the socket itself, into the multi-core framework. NVIDIA unveiled its plans for their own processor. You know, AMD has the license to use the x86 architecture. NVIDIA doesn't have that license, and they need a base to develop a host processor, and they chose the ARM architecture as their base. So ARM is the instruction set or the architecture that's used in most of the computers that we use today. Things like cell phones are based on ARM architecture, and their product is going to be based around that architecture as well. And we should see something from them in the 2013 timeframe. So much more integration of the processing into the chip itself, just as it has evolved in the past. We're going to see that evolution continue with the accelerator technology being embedded in the processor itself. So many changes are taking place on the hardware side. That's going to necessitate changes taking place in the software side. It's time to rethink our software and algorithms. It's a very disruptive technology, much more disruptive than what message passing was just a few years ago. You know, a few years ago we had to rewrite all of our applications to embrace message pass, sends and receives. And here we're going to have to do the same thing again to embrace the kinds of architectures that we're talking about, with the levels of parallelism that we have to deal with the constraints that we have in terms of data movement. So it's time to rethink and rewrite the applications, the algorithms, and the underlying software. When I think about this, these are the 5 topics that really get me excited, I'll say, about the opportunities and challenges that we have in front of us. We're working on something that we call synchronization reducing algorithms. We want to minimize the amount of synchronization that takes place during the execution. Thomas mentioned this in his talk, and I'm going to mention it again. We want to break the fork-join model that we have for parallel computing. Today, most of our computing is done based on loop-level parallelism. There's a loop where we fork things off, and then we join together at the end of that loop, synchronizing the computation. You can't do that when you have a million threads of execution. That's just going to destroy the performance in a way that's unacceptable. Communication reducing algorithms, we want to minimize the communication. My colleague at Berkeley, Jim Demmel, has championed this idea of coming up with a proof that shows that a given algorithm can be constructed with a minimum which has a minimum communication. You can't do any better than this for this particular algorithm, and then you go off and realize that algorithm in some software and enjoy the benefits of that minimizing effect. Mixed precision should be used more. Mixed precision is trying to exploit 32-bit and 64-bit arithmetic as much as possible. 32-bit arithmetic is twice as fast on conventional architectures in terms of the floating point execution rate, and you're going to be moving half as much data. So you get both benefits of the operations as well as the data movement in terms of speeding up the computations. So it's a real winner, and if you could exploit that in your computation using 32-bit arithmetic for the beginning of the computation to get an approximation, and then use 64-bit arithmetic to refine the solution or to compute a correction to that approximation. Reproducibility of results. This is something that some people find shocking or surprising, but in parallel, I can't reproduce the results, or I may not have reproducible results. And what I mean by this is I have a given problem on a given machine, and I run it today, and I take that same problem and same machine and run it tomorrow on the same data, and I get different results. So that can happen in parallel, because I can't guarantee the order at which I combine things. And when I can't guarantee the order at which I combine things, I may make small round-off errors in adding numbers up. So think about taking a sequence of numbers and adding them from largest to smallest, or from smallest to largest. Smallest to largest is going to give you a different result from largest to smallest. And the smallest to largest is actually going to be slightly more accurate in terms of the effective solution. So in a parallel setting, I can't guarantee the order at which things come together. The reduction takes place, and that says that I may get small round-off errors when I run it today or tomorrow. Those small round-off errors may be amplified if you have an unstable algorithm or you have a ill-conditioned problem. Both of those things can cause this this magnification of that round-off error. The magnification may be such that you actually lose the similarity between the two. So we really need to quantify the uncertainty at this level within our algorithm and try to understand better what the algorithm is producing and match that to the computation itself. But many people are surprised that we're going to get different results. And fault resilience, I mentioned, you want to have algorithms that can recover from failure, transition across failure, and continue executing without taking a performance hit in that way. So I just want to get to this issue about synchronization that Thomas touched on earlier. Today, we have a package called LaPack. This is the thing which followed on from the LaPack package. And it's organized in terms of its parallel processing in terms of a fork join level of computing. And basically what happens is there's a step of the algorithm where we basically do a sequential thing, and then we do a parallel operation, a matrix multiply, over this orange part of the computation. And you can characterize that as sequentializing things and then forking things off in parallel. And then the next step does it on a smaller size matrix where, again, you do the sequentialization and do the parallel processing, and you continue with that until you consume this. You consume the matrix. So that's a fork join. I think of it as a bulk synchronous kind of processing that's going on in this algorithm. It's very typical of many algorithms that we have today in the parallel space. And what we want to do is to break that. We want to unravel the computation in a way that exposes more things that could be done in parallel and does things perhaps on a smaller level of granularity. And what we think about doing is to breaking things into smaller tasks. We call them tiles. And we look at the tiles and look at how they operate on the matrix, in this case for this LU decomposition. And what happens is it's almost as if you take the algorithm and unwind it at the outermost level of the loop. When you unwind it at the outermost level of the loop, you expose the dependencies in the loop, and you end up with a directed acyclic graph that Thomas was mentioning that represents the computation. The critical path in this DAG is the longest path in the algorithm, and if you execute that critical path first, you'll expose the most parallelism. So what you want to do is to look at an algorithm, display the directed acyclic graph for that algorithm, and then execute that critical path as soon as possible, releasing as much parallelism as you can. And when you do that, you'll end up with very high performance on today's systems. You'll end up with a computation which is almost running in a very asynchronous kind of manner. We're exploiting this explicit parallelism that occurs. So this is a package that we're working on. It's called Plasma, Parallel Linear Algebra Software for Multi-Core Architectures, where we're trying to display or execute that directed acyclic graph for the computation, where the nodes in the graph are operations that are to be done, and the arcs represent the data dependencies between those graphs. Here's a cartoon that shows the kind of parallelism we can extract if we do a fork join level parallelism for a given algorithm. So this is, think of it like this, the colored boxes here represent active computation. The white space represents idle time for a given core. This is done on a 16-core system, and you can see a lot of idle time here with the basic loop level fork join kind of parallelism within the graph. When you express things in terms of a DAG, you're going to be able to schedule that, expose a lot of parallelism, and execute things in a much faster way on your system, squeezing out that white space. And you can see what happens when you do this on a large scale. So this is done on a 48-core node that we have at the university. Using these algorithms really reduces the synchronization, squeezing out that white space, allowing things to be executed much more rapidly, and overall being able to effectively do the computation in a much more direct way on these parallel systems. So we see a lot of future for these synchronization reducing algorithms. So all of this really is a call to action, in the sense that the hardware is changing very dramatically, while the software ecosystem remains fairly stagnant. We have the community codes that we have are really unprepared for the changes that are about to take place in the architecture. And in some sense, there's no global evaluation mechanism that we have in place to help us understand what components of the software stack are really missing and need to be focused on in terms of research activities. So we've put together something we call the Exascale, the International Exascale Software Project. It was formed a couple of years ago, and the goal is really to engage the international community to address some of the software challenges associated with exascale computing. We can't wait for exascale computing to do this. We need to start now in building up to exascale in terms of developing that software stack so it'll be ready when that hardware is upon us. So we're going to focus on open source software systems that allow for multiple platforms. We're going to try to share the risk and the investment that occurs between research groups and across country boundaries, and allow us to really leverage international talent that's out there in terms of deploying that software. So the idea here is to build this international plan for a coordinated research for the next generation of open source software for high performance computing. The current roadmap for Exascale has the following components. It has components that deal with system software, looking at the operating system, runtime I/O, external environments, software management. It has things that deal with the development environment, programming models, frameworks, compilers, numerical libraries, and debugging tools. It has applications involved in the overall evaluation of this in terms of being drivers for the underlying stack itself, looking at algorithms, data analysis, and scientific data management. And then there are some cross-cutting issues which really affect all of these areas, and they deal with resilience, power management, performance optimization, and programmability. So this group has been working for the last 2 years to build out this roadmap, and hopefully it'll be used to guide the kind of research that's necessary to work on software to get us to Exascale. So we see this International Exascale Software Project as sort of an overarching thing which can be used to provide coordination at an international level to look at various regions and to understand how we can manage the resources that we have and how they can be deployed for research and development and preparing milestones along the way. So we have participation across all of these groups and agencies in terms of this effort. So let me just conclude here and say that for the last few decades we always focus on the race car. We focus on the hardware of a computing system, and sometimes we leave behind some other components that are really necessary to make that race car work. And by that I mean, this HPC is composed of an ecosystem, and that ecosystem is made up of the hardware. It's made up of the compilers, the operating system. It's made up of the algorithms. It's made up of the numerical libraries, the message passing layers that are in our system. And we need to focus on looking at the research that needs to be done in all of those areas to maintain a well-balanced ecosystem for high-performance computing, not just look at the hardware. You got to remember that there's no Moore's law here for software or for algorithms or for the applications that we have. We really have to rely on an investment in terms of research to get us to that point. So with that, I'll end, and I don't know, do we have time for questions? No questions? No questions, okay.